chat box that my today's discussion will be on two topics. In the first session, one is called context and another is called quantifier. Okay, and these two topics are extremely important in mathematical logic, and they often build the podium on the basis of which, by standing on which, we can do our proofs. We try to write mathematical proofs. We try to write algorithms for computer program. Before discussing context, I shall first try to discuss about quantifier. Okay, so let's talk about quantifier first of all, and then I'm going to discuss about the context. Now, suppose you encounter with such a mathematical statement like for any integer, x square is equal to 1. Sometimes we encounter with such statements in mathematical proof. For any integer x comma x square is equal to 1, or this is one scenario. Another scenario is that there exists an integer x. There exists an integer x such that x square is equal to 1. Now you see, I have actually used two different types of words, two different types of sentences, and my common part of these two sentences are this: x square equal to 1. In one part I have written for any integer x, and in another part I have written there is an integer x. Now carefully observe that these two parts are actually not same, they are different. What it is saying? It is saying that if you consider the set of integer, which we basically denote by z, and we know that set of integer contains these elements 0, plus minus 1, plus minus 2, plus minus 3, and so on. So this particular statement is saying that for any integer, if you consider any integer, if you choose any integer from this set, that integer will satisfy this equation. Okay, which is definitely not true, because this equation is not satisfied by any integer. So we can know from our preliminary mathematical knowledge that this statement is false. Now, if let us study the second statement. The second statement is saying that there exists an integer x such that x square equal to 1. Now you know that when we solve this particular equation, we get x equal to plus minus 1. Now you see, plus minus 1 belong to the set of integers, and therefore you can actually have two solutions for this particular system, this particular equation. One solution is this implies either x is equal to 1 or x is equal to minus 1. Okay, if we substitute these two values in the equation, both of them satisfy the equation. Now when we talk about there exists an integer x, look at the word n. I'm only interested about finding at least one such integer, so I'm writing there exists an integer x. Now if a student says, okay, then if you are interested about only one integer, let me give you 1, then also I'm going to take his word, and this particular statement is meaningful. Suppose there is another student, he is saying, okay, you are interested in only one integer, at least one integer, I'm giving you minus 1. Then also the validity of the statement is true. So in all cases, you see that if I write there exists an integer, if I write this, then this particular statement becomes a true statement. So it is true. But the previous one is false, because the previous one is saying that it is true for any integer, which is not. Okay, so these two predicates actually are very important in mathematical proof writings. Okay, so this for is in some books you may encounter the word for all instead of for any. So these two words are actually same, for any or for all. Now these wordings, they are so often used that mathematicians have decided that okay, let us not write this statement, these two words again and again. Let us uh, invent a symbol for this. Okay, so they gave us a symbol for all. Actually, you see that for all, if I write it in caps, it becomes like this. Now they have chosen this A and they just inverted it, and this has become a statement. This has become a symbol, a very well known, universally accepted symbol, and we call it as for all. When we talk about there exists, okay, actually see, we can write this as, if we want to write it in caps, we write it as there exist, like this. Now what they have done, they have chosen this letter capital E and they just inverted it like this, and these two symbols have thus become two universally accepted symbols. So we call this as for all, and we call this as there exist. So these symbols have come from these words actually. Okay, now now I'm going to show you that when you are going to use this particular symbols in a mathematical statement, you have to be very careful about using it, because the wrong use of this particular symbols to a mathematical statement can give you a contradiction kind of thing. So you have to be very careful when you use these symbols. Say for example, instead of, as I just now discussed, that for any integer x, if I write for all x, this happens, then you have to, you know already that this is a false statement. And if I write, okay, there exists an integer x, okay, then such that x square equal to 1, you know this is true. So whenever you use these symbols, we have to be very careful. Now these symbols are actually known as quantifiers. They are known as quantifiers. So as we can see, there are two types of quantifiers. One is called one is denoted by this symbol, which is for all, and this is denoted by the inverted E, lateral inversion, which is called there exist. Now this quantifier for all is actually known as universal quantifier. It is known as universal quantifier, and the quantifier there exist is called existential quantifier. Existential quantifier. Let us now discuss about these two quantifiers, and let's see how the wrong use of these quantifiers lead to contradiction. Okay, so I'm going to move on to the next page for the discussion. Now suppose I'm writing for all x. I'm giving you two statements. My statement one is for all x there exists y such that x plus y is equal to 0. This is my statement one. And my statement two says that there exists y for all x such that x plus y is equal to 0. Now those who are new to those who are new to this type of mathematical symbols, they may think that the two things which I've written in statement one and statement two, they are same, but they are not actually. Let us try to look at this and let us try to understand what they do actually mean. When I write for all x, there exists y, x plus y equal to 0. Actually, I mean to say that for every integer x, there exist an integer y, there exists an integer y such that x plus y is equal to 0. And you know that this is a fact. If you look at the set of integers, and if you choose a 0, for instance, then for the integer 0, there exists an integer 0 itself, such that 0 plus 0 equal to 0. Now, if we choose the integer 1, for this integer, there exists an integer -1, so that 1 plus -1 is equal to 0. 2 plus -2 is equal to 0. 3 plus -3 is equal to 0, and so on. So from the knowledge of the set of integers, we know that this is actually true. But what does this mean? What does this mean? Let us try to write it in words. According to my symbol, it means that there exists an integer y. There exists an integer y such that for every integer x, there exists an integer y such that for every integer x, then x plus y is equal to 0. Now look at these two parts very carefully. What is it saying? It is saying that this integer y, carefully observe that this integer y is fixed. They are saying that this integer y is fixed. You are fixing any integer from the integer set, and when you fix this integer in the integer set, then for other integers present in the set, which we denote by x, when we add that integer to those integers, if I choose say for example 1 from the set of integers, then 1 plus y equal to 0, then 2 plus y equal to 0, then 3 plus y equal to 0, then 4 plus y equal to 0, 0 plus y equal to 0, -1 plus y equal to 0. It is saying that this integer y is fixed, and if you keep on changing the other integers x in the set of integers, then x plus y equal to 0 is always true. But we know that this statement is not a valid statement because it doesn't happen. How can we know this? Because we know it from our knowledge of integers. So we know that this statement is actually false. And this statement is definitely true. We have already seen such kind of things in the study of vector space and the study of group, definition of group, that this type of when we write the existence of inverse, we actually deal with this kind of statements. So therefore, this particular statement 1 is okay, no problem with it, but this statement 2 is not okay. So whenever you use this universal quantifier and existential quantifier, you be very careful about the order you choose. I'm not saying that it always becomes false. Under this particular assumption of the set of integers, it doesn't have any meaning. But if you change the domain to something else, it may become valid and this may become invalid. Okay, so I'm saying that I'm not saying that there exist cannot be preceded by for all. Sometimes there exist is preceded by for all, and sometimes for all is preceded by there exist, but you have to know what you are talking about. And that what you are talking about is actually known as the context. Okay, so let us now try to discuss the context for the time being. Suppose, as I can see, there are 55 students. Suddenly, a student enters into the class right now, and he sees that on the whiteboard, on the page of the whiteboard, I'm writing x square equal to 1. And I'm asking what is the solution. Okay. Suppose I have asked all of you that if x square equal to 1, what is x? Now he immediately, suppose he has started seeing from this particular page and he has not seen the previous pages. Then several questions can come to his mind. He can think of several possibilities. First of all, the first possibility is he may ask to himself, is x an integer? Because this can be a possibility. Then he may ask another question, that is x a function? Okay. Then there is another possibility, that is x a matrix? These are the questions which may come into his mind. Then he can ask, is x a subgroup of a given group? These several types of questions may come to his mind, because in this particular equation, I have not mentioned what I'm actually talking about. Okay. Now, suppose, as you already know, that this type of thing is, this particular statement is false and this statement is true. So I can rewrite this particular statement in the following manner. So for example, I can write the false statement. Let me write the false statement first. The false statement was, for all x belonging to z, for all x belonging to z, x squared equal to 1. This is false, you know, but still I'm writing it. And the other one, let me write, there exists x belonging to z such that x squared equal to 1. You know that this is actually true. But what is the difference between the earlier version which I wrote and this version? In the earlier case, we wrote that for all x, in this case, I'm saying that for all x, x squared equal to 1. Earlier version means this version I'm talking about. And there exists x such that x squared equal to 1. What is the difference between, let us consider this to be part 2 and this is part 1. What is the difference between this part 1 and part 2? In the part 2, something is not clear to us. It is not clear that what we are actually working on. Am I working on a matrix? Am I working on a function? Am I working on a subgroup? Am I working on an integer? That is not clear. But here, if a student starts reading from this particular page, it is clear to him that the context is the set of integer. And then he can declare that yeah, this particular statement is false because in integer, such a thing doesn't happen. Yeah, this is true because in integers, set of integers, these things happen. So this part which I'm writing over here, that for all x belonging to z, when the predefined knowledge of z is clear to us, that z is a set of integers. Okay, this type of thing is called context. This is called context. Context is the podium on the basis of which we actually study the truth or falsity of a particular statement. Okay, if we consider the case, say for example, if I write that, say for example, I'm writing that there exists, another example I'm taking, this is example 2 I'm considering. I'm saying that there exists a natural number, there exists a natural number n. Capital N is the set of natural numbers. So this predefined knowledge is there. Okay, so there exists x belonging to n such that for all y in what? For all y belonging to the set of natural number, x plus y equal to 0. If I write like this, you see that here the context is the set of natural number. What is the context here? The context here is the set of natural number. And in this particular context of natural number, this statement is never true. This statement is never true. This doesn't happen at all. Okay, this is always false. Again, if I write like this, for all x belonging to n, and this is obviously false in the case of integer also. But if I write for all x belonging to n, there exists y belonging to n such that x plus y equal to 0. And here also the context is set of natural number. Here also the context is the set of natural number. You can see in both the cases, this particular statement is true. These two statements are always false, because in the set of natural numbers, the number 0 is not present. We start from 1 to up to infinity, and therefore since 0 doesn't exist in the set of natural number, so there is no question that the other natural numbers will have their inverses with respect to addition. So in both these cases, where the context is set of natural number, the statements are false statements. So it is also false, and this is also false. But if I change the context to be a set of the integers, if I change the context to be a set of integers, then you know that this statement is false. This statement is false because it is not mathematically valid, but this becomes true because it is mathematically valid. So context is very important for the discussion of mathematical proofs. If the context is not clear, then your proof is not clear. All these things we are actually studying right now is because whenever we are going to write a proof, or whenever you are going to write an algorithm, you have to be very careful about the statements like for all and there exist, when to use for all and when to use there exist. This has to be very careful. This has to be taken care of by all of us. Okay, even with the we do the mathematics, we take care of this. You also take care of this when you write the computer program. Okay, now both of these statements, that for all and there exist, their negation, if we try to negate this, let us try to know that what actually comes out of it. Okay, so now I'm going to discuss the negation of the statements. I'm going to discuss the negation of for all and there exist. We are going to discuss the negation of for all and there exist. Now suppose, carefully listen to me, this part is very important. Suppose I'm going to study a property, which we denote by capital P, Capital P stands for the property. Now this property can be a mathematical property, this property can be a physical property, that property can be anything. We are going to study a property. Now I am writing under some context, that context is not important over here, because what I'm going to write is true for every context, because the result which I'm going to show you is true for every context. So under some context, I'm going to write this one: for all x, property P is true. For all x, property P is true. Now, if we want to study the negation of that, what we will get? For all x, the property is true. What will be the negation of this particular statement? According to the rule, the negation of this statement becomes there exists x not p. There exists x not p. You know that when we write this notation tilde, when we write this notation p, that actually means not p. Okay, so negation of this is not p. Remember this rule. This is rule number 1. This is rule number 1. Rule number 2, when we write there exists some y which satisfies the property p, and we want to study the negation of that, then that negation of there exists y property p, it becomes for all y not p. For all y not p. That is the rule number 2. That is the rule number 2. So you have to memorize these two particular rules. Negation of for all xp, which is actually equal to there exists x not p. The truth value of these two statements are actually same, and negation of there exists yp is actually equal to for all y not p. If you study the truth value of these two statements, you will find that they are actually same. Now I am going to apply these two things, these two results to a given mathematical statement. Suppose someone is writing a mathematical statement like not for all x there exists y, x plus y is equal to 0. Suppose I am trying to see what this mathematical statement becomes. Okay, so let us try to use this particular rule over here. Now suppose this implies, you see that whenever I am writing not for all x, so let us try to use it in terms of notation. Not for all x there exists y, x plus y is equal to 0. Now you know that not for all x, this actually become what? There exists x. So that means what? There exists x, and this becomes not p. So it is becoming not of this thing. There exists y, x plus y is equal to 0. Okay, and this gives what? There exists x. Now here I can use this not as not there exists y such that x plus y equal to 0, Now if I write this again, if you try to use this rule, what we will find? There exists x, and this not there exists y will become for all y. Not there exists y becomes for all y. So I'm writing for all y not p. Now what do we actually get? We get there exists x such that for all y not p. What is p? Here p is the statement which gives you x plus y equal to 0. So not p means this x plus y will not be equal to 0. Okay, I'm not saying right now whether this particular statement, which is the implication of the given statement, this is the hypothesis. You can say that this is the hypothesis under consideration, and this is the implication under consideration. Okay, now I am not actually verifying whether this hypothesis, whether this implication true or false. I am just trying to show you that how this implication is followed from the given hypothesis with the help of these given properties. Most of the people are going to face some sort of difficulties in grasping this particular idea, but once you are fully acquainted with this, I think you will be in a more feasible situation to deal with the mathematical proofs and computer algorithms. Okay, so I'm again going to say what I have done over here. Just look at this. Under some context, you can ask me that why this context has not been specified. Why this context has not been specified? Because in the previous page I have already told you that context has to be specified. Here I have written that under some context, that context may be the set of matrices, the context may be the set of animals, the context may be the set of people, context may be the set of numbers, anything. Here I have not specified the context because the rule which I was writing is true for every context. Okay, be it the set of people, be it the set of natural number, be it the set of matrices, whatever. Now, I have defined a property capital P. This property can be anything. Say, for example, if you write a property P that leopard has spots. Okay, now you know very well from this particular, this is a property, of course, because here the leopard is the animal, and you know very well from this particular statement that the context is the set of animals. Okay, so I am not specifying that this property should not be a mathematical property. This is any property. So if I write that for all x, this property is satisfied, what will be the negation of this particular statement? The negation is written as tilde for all xp. So what we do actually, that tilde for all x, that for all becomes there exist, because there exist is the opposite of for all, and this tilde is carried forward, and it precedes the property p, and p becomes not p. Okay, so not of for all xp, it becomes there exist not p. Okay, now I have tried to use this particular result over here. Now you know that for all x there exists y such that x plus y equal to 0. This statement is a true statement. This particular part is a true part. I want to find out what is the negation of that. So this particular statement is being preceded by not. So not, I'm writing it in the form of a symbol. So not for all x means this, tilde for all x inside bracket, there exists y such that x plus y equal to 0. Now you see that for all x becomes there exist. So I have written there exist x, and now this tilde is being carried forward and it precedes that part, this particular part. Now again, if I remove the bracket, tilde precedes there exist y. Now there exist y, tilde there exist y, it becomes for all y. So I'm writing here for all y, and tilde is further carried forward and it precedes the statement, which here this mathematical statement is x plus y equal to 0. And we write there exist x for all y such that not p. And you know, if p is x plus y equal to 0, then not p will be x plus y not equals to 0. So what does this particular statement is saying? That then what is the negation is saying? The negation is saying that, let us try to write it in words. The negation, this part is saying that there exists an integer, x such that for every integer y, then x plus y not equal to 0. Try to think about this particular statement. What I'm saying, this particular statement has been obtained. Why did I write this statement? This statement has been written from this particular expression. So what does this statement means? The statement means that there exists an integer x such that for every integer y, x plus y is not equal to 0. And obviously, you know, if you think of it, that this particular statement is actually a false statement. This part was a true part, its negation is false. Okay, now if I try to write the state, now if I consider the statement which was actually false, there exists y for all x plus y is equal to 0. What will be the negation of this statement? Let us try to quickly write. The negation of this statement will be there exists y for all x plus y is equal to 0. This implies there exists y, negation for all x plus y is equal to 0. this implies there exists y, and sorry, this part will be for all. This part will be for all. So for all y, and this will be there exist x, such that negation of x plus y equal to 0. This implies for all y there exists x plus y not equal to 0. This part is a false statement. This part is a true statement.